So we have four German conferences, Monday, mail staff, very true. And got the invite the personal numbers that all line, some of line, and we can vote for this agenda. So please vote. Okay. So let's start. So please go ahead.
Начнем с анкеты, да? Хорошо. Characteristic of Nurdaulet Shynarbek. Nurdaulet Shynarbek was born on 2 March 1999 in Taldykorgan. He completed his secondary education at the Kazakh-Turkish High School. From 2016 to 2021, he studied mathematics at Nazarbayev University and obtained a Bachelor of Science degree. From 2021 to 2023, he completed a Master of Science degree in mathematics at Süleyman Demirel University. Since January 2024, he has been pursuing a PhD in mathematics and statistics at SDU University. During his professional career, Nurdaulet Shynarbek has worked at SDU University in several academic and administrative positions. He has served as an assistant instructor, senior advisor, coordinator of the mathematics educational program, and teacher researcher. Nurdaulet Shynarbek has 7 scientific publications related to the topic and research direction of his doctoral dissertation. 7 scientific publications. Thus, his dissertation-related research output includes 2 Q1 and 2 Q2 journal articles indexed in the Web of Science and 1 Q2 and 1 Q4 journal article indexed in Scopus, and 1 paper in international conference proceedings indexed in Scopus. Nurdaulet Shynarbek also participated as a research team member in the state-funded scientific project, Defountain Approximation and Irrationality of Mathematical Constants, funded by in 2023-2025, funded by the Ministry of Science and Higher Education of the Republic of Kazakhstan. Nurdaulet Shynarbek is married and has a son. He is Да. His educational background, publication, record, participation in a state-funded scientific project, and personal qualities provide a strong foundation for his further academic and professional development. This is characteristic of Nurdaulet Shynarbek.
That's all?
Да. Есть вопросы по анкете?
So, no questions to the secretary. And now we can begin the defense, I think. So you have 25 minutes.
So, can you hear me well? Yeah. That's fine. So good morning, everyone. So my name is Nurdaulet, and today I will be presenting my PhD dissertation work that is related to computational and analytic approaches in generalized continuous fractions. That was done from 2024 January till 2026 June. So we are doing it in 2.5 years. So my local scientific supervisor is Professor Shirali Kadyrov, while my external supervisor is Professor Francesca Sica. So I think we may start. So overall outline for today's presentation is given by background and research problem. Then since I'm defending only based on the series of publications, so our results is present in form of 3 articles. First article is considered a difference equations and 2 identities related to pi square based on that, which was published in Journal of Interdisciplinary Mathematics, Web of Science Q2. And our next paper is devoted to polynomial continuous fraction for log2 and its generalization, which was published in Arabian Journal of Mathematics, also Web of Science Q2. And in my opinion, the strongest results is our third paper, which is a parametric polynomial J fraction for pi square, which was published in Electronic Research Archive Journal, which was published by American Institute of Mathematical Sciences, which is Q1 in Web of Science. And at the end, we will conclude by contribution and overall conclusion. So I think first we can start about what is continuous fraction. So continuous fraction is simply writing a number by repeatedly fractions. So this type of writing is very useful in rational approximations. And that's why this is what it makes it interesting in number theory and particularly in approximation theory. And overall, the form of general continuous fraction you can see from the box here, where x is a number and b0, a1, and nested fraction is representation of continuous fractions. And in more compact form, we can say that it can be written as b0 plus continuous fraction of an divided by bn. And if you truncate at any given point, at point n, for example, then xn is given by b0 plus an divided by bn from 1 to n. And as a result, we are getting convergence that is represented by numerator an divided by denominator bn. Okay, said that, I want to present 2 most famous examples of simple continuous fractions. So as you may see, the first example is √2, and the another example is pi. So if you look for an example with √2, you can see that numerator is always 1 and denominator is always 2. And we can easily see a pattern here, which is very interesting, and its finite truncation approximations is given by 1, 3 divided by 2, 7 divided by 5, and so on. And another representation for pi is also simple continuous fractions, and we call continuous fraction simple if its numerator is always given by 1. Okay, so for pi, what we see, for pi, we don't see any visible pattern here. That's what it makes it very hard to study, and what makes the proof of such kind of continuous fraction hard. But simple continuous fractions were studied a lot in later terms. So in this dissertation, we are mostly focused on generalized continuous fractions. And generalized continuous fraction, both our an and bn can be given by sequences, by functions, by whatever we want. And we choose an and bn so that our finite truncation are well-defined. By well-definedness, what we mean is that convergence, especially denominator, should not be equal to 0 at any given point. And by convergence, we mean that if you truncate at any given point, then we will get a rational version, which is an, capital An divided by capital Bn. So we will work very closely with this convergence in our later publications. And this was the introduction to generalized continuous fractions. And in this dissertation, we are mostly interested not on generalized, but inside of which we are interested in polynomial continuous fractions. The very interesting things about polynomial continuous fraction is that both an and bn, in our case alpha n and beta n, is given by polynomial functions. Yeah. So what makes polynomial continuous fraction interesting is that for one constant, we can have infinitely many representation of different polynomial continuous fractions. And said that, it means that the convergence of this different polynomial continuous fraction also differs by speed. And this is how the Apri in 1978 proved that zeta3 is irrational. So he found a polynomial continuous fraction representation of zeta3, and it turns out that the speed is so high that it's enough to prove the irrationality of zeta3, and that's why we got interested in this topic. And this topic was also exclusively studied by Henry Cohen, which is a very big professor in this field, and mostly I can say that he is a father of computational number theory approach. And whenever we are talking as a polynomial example, you can see an example here where alpha n is given by formula 2n cubed multiplied by 2n minus 1, and beta n is given by 5n squared minus 4n plus 1, and its representation. So this is one of the very famous polynomial continuous fraction, and it converges to 18 divided by pi square. All right, so it converges to 18 divided by pi square. It's very famous, very old. And the motivation of this work was that from 2019, Israeli researchers from Technician University introduced a project called Ramanujan machine. So what Ramanujan machine tries to do, like inspired by Ramanujan, he tries to find polynomial continuous fractions that can be represented by any constants. So they want to find, somehow they want to build a machine, the algorithm that finds polynomial continuous fractions for mathematical constants. So, and they were successful enough so that in 2021, one of their big papers with a lot of conjectured formulas got published in very good journal in Nature. So, which give us very inspired. We get very inspired by that and try to prove that conjectures. And also from other side, we have a very big professor who is in his late 80s called Henry Cohen, who built a program called Paris. Now it's called Paris GP, where mostly computational number theory, elliptic curves, algebraic number theory is simulated and done in that code. So a lot of experimentation was done in Paris and GP, and I can say that he's the father maybe of computational number theory. And for creation of Paris and GP, he get a lot of awards both from America and in France. And he recently published a database of continuous fractions that contains more than 1,700 polynomial continuous fractions that represented by constants, that represents constants. And he says that more than 1,500 of them are still unproven, are still conjectural. So what we have that Ramanujan machine generates conjectures from one side. From other side, we have Henry Cohen, who does analytical proof of that. And also he found using his Paris GP code more than 1,700 polynomial continuous fraction representations. And we were interested in that. And a lot of work has been done in order to prove these conjectures. But the problem is that they were proving the isolated cases of polynomial continuous fraction. But in this dissertation, our aim is not to prove the isolated cases, but we want to try to generate a method, some approaches of how several types of continuous fractions can be proved by that method. So we are trying to find a method of how all these continuous fractions, at least most of them, can be proved, approached, evaluated, and if you are lucky enough, generalized into a parametric family of continuous fractions. So this is how we get interested in that. And the interesting thing is that continuous fractions is closely related with second order difference equations. So mostly what we say is that difference equations is a discrete version of differential equations. And in both cases, what we know that if second order differential equations is given with constant coefficients as an and bn, it's very easy to solve and try to find the closed-form solution very easy. But whenever we have bn an as a variable coefficient, it becomes much harder, and sometimes it becomes even impossible to evaluate that. And it turns out that our continuous fraction is very closely related with second order difference equations, where an, which is numerator, is given by bn an minus 1 plus an minus 2. Where bn is given with the same formula, but the main difference between these two is that their initial values are different. Okay, that's why we need to approach it differently. And the main idea is that whenever we are trying to prove, evaluate, or generalize continuous fractions, first thing that we should do, we should try to understand these recurrence relations, both an and bn. So said that, I want to move to our first paper. And in first paper, we were studying a second order difference equation. And firstly, we studied a non-homogeneous case where a difference equation is given by formula yn minus bn yn minus 1 minus an yn minus 2 is equal to some fn. Okay, and we found a closed form solution for this kind of second order difference equation. But I want to tell that we found it whenever we set our bn and an as cn plus dn plus 1, and an is represented as minus cn dn. So we are not considering that we solved all the difference equations, but we solved a specific class of difference equations. Okay, so this kind of work were extensively done by Malik, but our approach and our solution is different because we give a method of how we can find a suitable Cn and Dn and how it can be applied into continuous fractions. So the idea of how we prove that was that what we try to do, we try to factor second order difference equation as a multiplication of two first order difference equations. That's why we need Cn and Dn. So if you're likely enough to choose Cn and Dn, so that it factorizes into two multiplication of first order difference equations, then we can easily solve two first order difference equations, and based on that we can find a closed form solution. So as you may see from the slide product of two first order operators, here we have capital DD and capital DC, where these are the two first order difference equation, and multiplying that we can evaluate two first orders and get a closed form solution. And if now, until now we were considered non-homogeneous case, now if you move to the homogeneous case, what our closed form solution gets a little bit simpler, and it's represented by this formula. And if you take that, our D1 is equals to y0 divided by y minus 1, which is initial cases, then our closed form solution gets even simpler. So now the important part is how it's related to continuous fractions. So as I told, so our bn and an is represented as a product and as an addition of cn and dn. And from the first equation, what can we do? We can represent cn as an divided by dn, and then we can put that into dn plus 1. So my dn plus 1 is also a first order recursive equation where dn plus 1 is equal to bn plus an divided by dn. So if I can represent dn plus 1 by dn, it turns out that I can represent dn by dn minus 1, where dn minus 1 by dn minus 2, and I continue like that until we reach the initial conditions, and at the end we get a finite continuous fraction form. Okay, so applying that into continuous fraction form, we have proved two conjectural continuous fractions. So first one where bn is quadratic and an is given by quadric case, and it turns out that it converges into 8 divided by pi square. And our another theorem is that bn given by, again, quadratic and an being quadric, it converges to 18 divided by pi square. Yeah, so this is the main result of our first paper. So what we did in our first paper, we took a second order difference equation, we systematically studied it, and we applied it into continuous fraction and derived it and proved it to conjectural continuous fractions that was conjectured by Ramon-Jean machine in their Nature paper. Now I want to move to our another paper, second paper, which is related to polynomial continuous fraction representation of log 2. And firstly, I want to state the main theorems that we have here. So if our bn is equals to 3n plus 3 and an is represented by minus 2n squared, then its polynomial continuous fraction equals to 1 divided by 2 log 2 minus 1, where log is natural logarithm. So the approach is of how we prove this identity is that in this case we are studying both convergence an and bn. So first what we do, as we know that an and bn both represented with the second order difference equations, and we were lucky to find a closed form solution for an, which is represented by n plus 3, 2 to the power of n plus 1 factorial. But unfortunately, we were not able to find a closed form solution for bn. That's where we have an educated guess, and we call it ansatz. So we say, let us bn be represented as an multiplied by some function, sum of some functions, where ck is represented as with this formula. Now the only thing that we need to do, we need to prove that sum of this ck is equals to 2 log 2 minus 1. If it's equals to, then we proved that this continuous fraction converges to that. So what we do, so we take a limit of an divided by bn, and at the end it converges to that. So the first thing that we need to do, again, as I told, we need to somehow prove that this summation of this function is equals to 2 log 2 minus 1. That's why what we did, we take some formula for log 1 minus x, and instead of x, we took 1 over 2, and taking integral 2 times allowed us to get a closed form solution, or this summation formula for 2 log 2 minus 1, and proved that. We also proved that Bn is given by this formula, and its limit converges to 1 divided by 2 log 2 minus 1. So this is our main result. So we proved a conjecture that was, again, proposed by Ramanujan machine, but not only that, we have been able to generalize it into a parametric family. So parametric family means that instead of m, we can give any number, and we will get another representation of log 2 with a different speed. And if the speed is close enough, so we can prove the irrationality of that constant. Unfortunately, in this case, it is not enough to prove it, but the idea is that studying these kind of parametric families allows us to prove the irrationality in some cases. So here what we have is bk is equal to 3k plus 2m plus 2, where ak is minus 2k multiplied by k plus 1. And then we get a polynomial continuous fraction representation. Its polynomial continuous fraction representation converges to minus 1 to the power of m divided by log 2, and sum of minus 1 to the power of k plus 1 divided by k. So this is what it converges to. So now this is, here we have two corollaries, two first representation of that parametric family. So we selected first two, and this is what it is. And now we are done with our second paper. I think now we can move our third paper, which is, in my opinion, is the strongest result. So as I told, Henry Hokan was a very famous, very powerful professor in number theory, especially in analytic and computational number theory. In one of his recent papers, he proposed a conjecture into a parametric continuous fraction that is represented by an and bn, as you may see formula. And he suggests that this polynomial continuous fraction converges to pi squared. He didn't exactly say to which value of pi squared it converges, but what he says that most probably it converges to, and we tried to prove it. And the problem with this approach is that both in an and bn, what we have a very high degree. So an is represented by second degree n to the power of 2, and bn is n to the power of 4. Then what it means that convergence an and bn grow very fast. So very fast, and just finding a closed form solution becomes very hard for that. That's why we need another approach of how we can solve this question. And we have been able to solve this question, and the main theorem looks very beautiful. We get a very beautiful result where xn or xu is represented by a binomial series of 2u u cubic pi squared divided by 18 plus some rho u, where rho u is some rational number. Okay, and the exact value of rho u is given by first order difference equations. So it turns out that everything in this dissertation is related to Recon's relation. Right? We also found a closed form for rho u, but overall this is the main formula. And here we have the first values of representation for whenever u equals to 1, 0, and 2. So if you look to formula, it looks very aesthetic and very beautiful. So we didn't expect that we will get that beautiful result, but unfortunately we get it. And the interesting thing is how we proved that, and the approach of how we proved that. The first thing that we should do in order for this continuous fraction to be well defined, we need to study the denominator qn that is represented by qn. And what we know is that qn shouldn't be equal to 0. Okay, we should prove that, but we have been able to prove the stronger results and we proved that qn is more than 0, which means that qn is never equals to 0. And also, since we know from the difference of two consecutive terms of convergence, then qn is represented as an 2n factorial multiplied by some polynomial p. And what it means, in order to make our life easier, we divided, or we normalized our polynomial continuous fraction and its recurrence relation by dividing into 2n factorial. So, and taking the difference of two consecutive terms, we arrive to a result where xn minus 1 is given by this formula, where the left part of this formula is a known part for pi square, and the right side is coefficient related to u. And the problem here is that for every u, I should prove that there exists a polynomial p such that this can be separated into two parts, where first part is related to pi square, another part is numeric. Yeah, so it was very hard to do that because we can prove it for several u's. So what we did first, we proved for u equals to 0, then u equals to 1, u equals to 2, and it turns out that our polynomial p is given by a polynomial with degree of n to the power of 4u, which means that if u is 1, then it's a polynomial of degree 4, if u is 2, polynomial of degree 8, and so on. And we made a numeric check. I think we ran computer for 3 days and we reached u equals to 103. And it turns out that we have a polynomial of degree 412, which is very big. And from here, we were thinking that what if we can prove that there exists p for all u? Yeah, so what if it looks like there exists p for all u? What if we can somehow prove it? And also we find out that u is degree of 4u, and we were thinking, what if we can construct a raising operator such that results of convergence of u plus 1 can be represented by a result of convergence in u. So here, where we propose the raising operator, and as far as we know, it's have been never proposed till now, and we are the first one to do that. So if you look to proposition 18, so we can see that after normalization, the second order difference equation is given by this formula, where we have 2n multiplied by 2n minus 1 multiplied by p hat u, and so on. And now we need to just to prove that we can always find pu. Yeah. So it turns out that it was been very hard to do that. Now what we did, so if you take a summation from both sides, if you take sum from both sides, then what we know that it's telescoping, and on the left side only xn will stay, and on the right side will stay the sum of this function. And what we proposed if u plus 1 can be represented by a formula that we found for u. And if you continue like that, we can start with an initial value and we can make an induction and prove that it exists for all u. And so that's why we define it psi u fn, which is given by a0, which is normalizing, stabilizing polynomial of degree 3 multiplied by fn plus a1 multiplied by fn plus 1. And our polynomial raising operator is given by lu plus 1 psi f equals to bnu, which is also a normalized stabilizing function multiplied by luf and plus cn multiplied by luf. So what we are moving, we are sending solution in luf into lu plus 1f. So if we have a function and it exists for lu, it turns out that it exists also for u plus 1. And this way, just having induction, we prove that it will exist for all u. So now what we do, now whenever we prove that polynomial exists, we need to somehow evaluate that. And whenever we were trying evaluating that, we need we found a telescoping formula. So su plus 1 minus lambda u multiplied by su is equals to theta u minus theta u n plus 1. So by taking sum of that, it turns out that theta u minus theta u n plus 1 is represented as theta u1 minus theta u n plus 1. And from the formula for su, we can see that the denominator grows much faster than the numerator, which means that theta u n plus 1 approaches 0, right? So we can just say that it's 0, and our closed form solution is represented by theta u1. And here are the first 3 identities of our parametric polynomial continuous fractions. So which is, if u is 0, it is famous pi squared divided by 18. So if you remember in our first paper, we proved polynomial continuous fraction for 18 divided by pi squared. Here we have a vice versa. And x with u equals to 1, we have 4 pi squared divided by 9 minus 13 divided by 3, and so on. So what it shows that this parametric polynomial continuous fraction is a rational multiplication of pi squared plus some rational correction, but some rational number, which is not really interesting. So with this point, we are done with our paper number 3. And now I want to state the main novelty statement, what we did. So the novelty of this study is that we didn't just evaluated some isolated cases of conjectured polynomial continuous fraction, but instead what we did, we developed a recurrence-based mechanisms that can be applied to prove several families of polynomial continuous fraction and can be applied into a wide range of polynomial continuous fractions. And especially, I want to tell that in our first paper, we find a closed form solution for second order difference equation with variable coefficients and applied it into continuous fractions. In our second paper, we found an explicit convergence and generalized it into a parametric family. And in our third paper, we introduced a raising operator and a telescoping in order to evaluate chi-square family. So main conclusion is that in this dissertation, we have established 3 different methods of how polynomial continuous fractions can be approached, evaluated, proved, and in some cases generalized. And the final message is that these mechanisms not only makes evaluation of some parametric polynomial constant, but also gives us the way of how we can generalize it into a bigger family. Yeah. So, wait. Yeah, so mainly we are done, I think.
Okay, thank you. Are there questions? Okay, if we have no questions, we can proceed further. And what is on the agenda? So we have our local supervisor. Вопросы имеют? Окей.
Да, конечно.
Все. Я хотел спросить, вот мы несколько репрезентаций вот этих чисел иррациональных нашли, да? Ну, полиномиальные вот эти фракшн. Я хотел спросить, а можно ли как-то, не знаю, обобщить эти результаты? Ну, например, сделать для их суммы или для их умножения?
Да, можно. Что можно сделать? Например, Раманжан машин, о котором мы говорили, нашли polynomial continuous fraction representation для z3 плюс z5. Это было, в принципе, давно известно. Также есть, например, полиномиальный continuous fraction для e to the power of p, e в степени p и так далее. Вот такие можно их делать на умножение всяких констант, их суммы, но вообще сама
А
идея...
между ними умножать можно, да?
Да, можно.
Тоже можно.
Ну, можно, но это сложно. Но сама идея of continuous fraction, сама идея заключается в том, чтобы мы получили, чтобы мы смогли доказать иррациональность каких-нибудь констант, чем Раманжан Машин и Кохан занимались, как последователи Апери. So, сейчас пытаются, что они пытаются? Пытаются доказать, что Z5, Z7, Z9 тоже иррациональны. Вот этот метод. И этот метод самый многообещающий, так сказать.
А бывают какие-то иррациональные числа, которые такие презентации не имеют?
Нет, таких не встречал. То есть, как минимум, любую можно превратить в обычную continuous fractions. Скорее всего, можно в полиномиальную превратить. Потому что все константы, которые я знаю, имеют полиномиальную continuous fractions.
Это сложный вопрос.
Да. Можно вернуться на 15-й, по-моему, страница была?
Конечно.
Да. Вот тут в CK там на знаменателе там 2 степени k минус 1 есть.
Да.
Из этого он не перестает быть полиномиальным?
Смотрите, вот CK это просто сумма. Что мы пытаемся делать? CK это не continuous fractions, то есть не цепная дробь. То есть мы пытаемся доказать... Ой, Извините, мы пытаемся доказать, что цепная дробь, которая represented by bn and an, сходится к константе 1 делить 2 log 2 минус 1. И для того, чтобы это доказать, мы имеем дело с convergence an and bn. Да? И сама идея заключается в том, что мы нашли closed form solution для an, и теперь, если мы найдем closed form solution для bn, просто взяв лимит n до бесконечности, мы можем доказать, что она convergence to 1 делить на 2 log 2 минус 1. И вот, и тут основная мысль, может ли логарифм be represented by суммы от ck, где ck вот эта формула. И мы это доказали, взяв 2 раза интеграл from both sides. Лемма 11.
Хорошо. А для π раньше было известно, правильно?
Да.
Тогда и умножать можно. Значит, для π квадрат тоже известно, правильно?
Да. Для π куба, π в четвертой степени известно. Но из-за того, что уже известно, что они иррациональны, это не особо интересно людям изучать вот эти темы. То есть в основном мы пытаемся изучать то, что насколько быстро он convergent to given constant. Если он достаточно быстрый, that's proof irrationality. То есть тут вопрос или доказательство того, что она иррациональна, или эстетики, да? Найти какой-нибудь полиномиальный категорий, который очень красивый. Да.
Спасибо.
Yeah, I can make one quick comment. Basically, if I understand your question. Okay.
Нет, он может разговаривать.
So basically, if you have a representation of pi, and you have another representation for, let's say, log 2, if you multiply, it's not clear what is the representation you get. It's hard. I mean, just because you have two representation, if you multiply, there is no formula that gives you a nice representation. So that's a challenge. It can be done, but it's not obvious in itself.
I want to ask some questions as well. Can you hear me?
Yeah, I can hear.
Oh, okay, good. So using your methods, can you give some presentations for zeta functions?
Some representation to zeta functions?
Yes.
You mean? Actually, yes. So we have a paper that is related to three new parametric family representation for zeta 3. It's still unpublished, but we created and proved a 3 new parametric family for zeta 3. Yeah, that comes from Euler type continuous fraction representation. So actually we can, right?
Okay, so can you prove that zeta 3 is irrational using your method?
Yeah, so if you're talking about that new 3 representations that we found, unfortunately they cannot prove that zeta 3 is irrational. They only give some new parameters, some new representation of that, but its speed is not fast enough. Yeah, to prove irrationality.
And for which constants can you prove irrationality using your method?
So for now, the main question is about the irrationality of Catalan constant. Yeah, so we also have a paper that is still unpublished that related to Catalan constant, and polynomial continuous fraction representation of Catalan constant is still conjectural and has not been proved yet. And we proved that, but its speed is also not enough to prove the irrationality. So we proved 2 families that they converge to Catalan constant, but speed is still not enough. So it's still a big question if it's irrational or not. But people say that most probably it is irrational.
Okay, and can you do zeta 5, like a continuous fraction representation of zeta 5?
Yeah. So for zeta 3, for zeta 5, for zeta 7, we have a standard representation of polynomial continuous fractions. But the problem with that, the higher the degree gets, so higher the an and bn gets. So for example, for zeta 3, an is degree of 6 and bn is degree of 3. Polynomial, I mean. For zeta 5, an is degree of 10 and bn degree of 5, which means that working with convergence an and bn becomes extremely hard because they're increasing very fast. So that's the main challenge. Normally we have one representation of this constants, but they are not proving irrationality.
Okay. So another question is about papers. As you don't have a dissertation, you just have papers, and as I see, all your papers are co-authored with other people. So what can you highlight? What were your contributions?
So let's start from the very first paper, the second order difference, when we proved second order difference equations. So my main contribution was that I helped to find a closed form solution for a non-homogeneous case and helped converting it into polynomial continuous fractions that represents a constant. In log2 cases, I helped proving that series CK converges to log2, and also helped generalizing that family into a parametric family. And third paper is mostly I have done most of the things. So I think like 90% was done by me, right?
Ну, вот у меня к членам комиссии вопрос. Вот здесь с формальной точки зрения то, что вот презентуется без диссертации и на основе там 3 статей, то есть это там формально выполнены эти критерии? Ну, причем статьи там в соавторстве там с несколькими людьми.
Я не услышал вопрос. Плохо слышно. Можете повторить, пожалуйста?
Вот вопрос по
Я
поводу...
отвечу на этот вопрос. Я отвечу на этот вопрос, да. Докторант выходит как бы на защиту по серии статей, и у него имеются 3 статьи, которые удовлетворяют условиям защиты. Все 3 статьи и удовлетворяют условиям защиты.
Ну, то есть по этим 3 статьям можно не писать диссертацию, так, да?
Да. Если имеются 3 статьи, которые удовлетворяют условия защиты, можно не писать диссертационную работу. Просто предоставить серии, то есть список статей, серии.
Поэтому, да, диссертация вот так выглядит.
Да.
Да, я тоже заметил, что он какой-то странный, там каждая глава как будто одна статья.
Да, там 3
Ну,
статьи.
вообще, да, вообще было бы лучше, конечно, видеть диссертацию. Вот, и вот он говорил про те же результаты, которые не включены в эти статьи, есть также у него диссертации, которые он мог бы включить, в принципе, тоже.
Ну, тогда бы
это было бы
надо
как бы
было ждать,
лучше.
когда они выйдут. Тоже вопрос такой спорный.
Не, в диссертацию можете их включать, несмотря на то, что они не вышли также.
Ну, вопрос, вы на защиту результатов, которые не опубликованы, тоже довольно странно.
Да нет, это нормально.
Ну, в общем, это такой, смотрите, это такой вопрос, поскольку положение разрешает защиту при выполненных условиях, и вообще говоря, ну, мы можем оценить это, то, я думаю, здесь нет никакого такого вопроса серьезного.
Как я ранее уже сказала, вообще-то докторант имеет 7 статей, из них вот 3 предоставил он для защиты. То есть вот эти 3 статьи удовлетворяют условиям защиты. Но у него есть еще дополнительные работы, тоже относящиеся к этой теме. Есть вопросы по работам? Публикаций достаточно, я могу сказать.
Так, еще вопросы есть с диссертантов? У нас еще будет в это время для дискуссии, да?
Нет, это основная...
May I ask question?
Я уже просто отстал от жизни.
Simple question.
Это, да, другие члены диссертационного совета можете задать вопросы. Это у нас основная часть. Вопросы и
May I
ответы.
ask question?
Да.
Yeah, maybe it is a simple, stupid question, but I don't know. I'm wondering that we know that continuous fractions might be periodic and non-periodic, right? And I just want to know that how that periodic continuous fraction affect on convergence of your polynomials, or maybe it doesn't affect on that. I don't know.
So mainly we have a periodic continuous fraction. So we have actually one paper related to periodic continuous fractions, and in periodic continuous fraction is mostly represented when we have an irrational number. For under root 2, under root 3, it comes mostly in that kind of numbers, and it's already known that they are irrational, so like they make no sense. But whenever we are talking about polynomial continuous fractions, they cannot be periodic. Why? Because n starts from 1, then in next term it becomes 2, 3, 4, and so on. So it's only increasing, right? Yeah, but periodicity mostly met in like under root numbers. So for example, I seen case here, I seen root 2, and like even if it can somehow prove that it's irrational, like it's not interesting. Why? Because it's already known that it's irrational, right?
Next question. What next open question remain that you would like to study in your future?
So normally now, as I told, we have papers related to zeta3, Catalan constant, and now before this big work in this dissertation, the aim was to somehow try to prove the irrationality of zeta5. It turns out that it's very hard, and we've been unable to do so. But next question is still if we somehow can prove the irrationality of that constant, right?
Okay, I have one question. Is it reasonable to consider functional instead of polynomial continuous fractions? So we have not a polynomial function, but maybe some power, say 2 to the power n or something like this. What is known?
So actually we can do so, but like I don't see that we need to do that. Why? Because like the beauty of number theory is that we are talking only about numbers. We are care mostly about integers, and that whenever we take functions and we take some rational representations or function to the power of some big powers, then it becomes very hard to evaluate. Normally, if I'm not wrong, there is paper there is some research that was done in this topic by Vadim Zudilin and his co-authors, but I don't see that this research type is developing or going somewhere. Like it was done and looks like it doesn't, or it wasn't interesting much, and that's why it stopped. Right.
Okay.
Can I ask one more question?
Uh-huh.
Is this representation for P polynomial or not?
No. It's simple continuous fractions.
It's not polynomial.
No, not polynomial.
Is it possible to transform it to polynomial?
Exactly this one, no. But overall, we have a polynomial continuous fraction representations for pi. Yeah. So one of papers of Shirali Kadyrov professor has a polynomial continuous fraction representation for pi and e, and they have proved some conjectures in 2019, I think. But just moving from simple to polynomial is impossible as far as I know.
Другие вопросы? Other questions?
Yes, I have questions. Can you hear me?
Yeah.
Okay. Nurdaulet, that was nice presentation. I have some small questions. The first question is, you said in the first paper, the second order differential equation, and you convert it into a difference equation, and then your method would obtain closed form solution. So did you solve some equation whose solution was unknown, or your methods were applicable to only to the known equations whose solutions were known?
I think there is some problems. Like I didn't hear your question well, but if I understood correctly, you are asking about the different equations that where Bn and An is represented as addition and multiplication of Cn. Yeah, so it is not working for all difference equations, unfortunately. It's working for a separate class only of these continuous fractions, where we can divide An and Bn into this kind of two polynomials Cn and Dn. So if it is possible to divide, then we can easily transform it into polynomial continuous fraction and we can easily evaluate that. But if it is not, then it needs another method. So for example, in paper 2 and 3, it was impossible to divide into such kind of Cn and Dn. That's why we proposed another methods of how we can try to approach this kind of problems.
Can you just show me the slide number 23?
32, you mean?
23.
Yeah.
Yes, if you notice in theorem 19, I saw one thing, the fixed pi square term. This is independent of u. So is there some specific reason? I always see in your results that the term with pi square is independent of u, because this difference depends on n and u. So is there a specific reason that this guy is always independent of u?
So sorry, I because of some sound distractions, I didn't hear well your question.
Can you see that there is a term, fixed pi square term?
Yeah. So
this is independent of u. This does not depend on you. So there's a specific reason.
So So if I understood correctly, so you are trying to ask if our pi square is independent of u, right? Pi square.
Yes.
Representation. So actually, that's what we wanted to prove. That's the main part. So if you move to the so this part in lemma 17, it is widely known that this series is represented by pi squared divided by 18. And another part was that if we been able to find pu such that it will not affect pi squared, such that it will not create another constant, or such that it will not create some another function, so that it will always stay rational multiplied by pi squared plus some rational. So we were testing if we always can find such kind of pu, and it turns out that we can find, and we can prove that we can always find such kind of pu for all u. Right.
Okay. Thank you very much. Thank you.
Other questions?
Maybe I have one more question. So, congratulations, Nurdaulet. It's good work.
Thank you.
I just have one question related to the applications of the approximations of log2. You probably are aware of the applications of log2 in computer graphics and chip design and those things. Did you look at the continued fraction approximations already existing in the literature for log2, and how your approximation fare with them? And if you try to make an approximation algorithm, would it be possible to look at the complexity of that algorithm?
Yeah. So normally we have as we know, so we created one family of representation for log2, and there is many others. So we also have another paper, sorry, on that, when we tested several families for log2 and learned that. And the beauty is that we can study the speed of convergence. So as you said, complexity, we can do that. And the difference is that whenever we are talking about polynomial continuous fraction, and especially about parametric polynomial continuous fraction, that depending on the parameters, the speed of convergence differs. So what can we do? We can say that let's truncate at any given point, for example, at point 10, and the truncation error, or the error, should be this kind, for example, 10 to the power of -5. And we can always find a parameter such that makes this situation to be possible. So just truncating at any initial point, we can find the best approximation and suitable approximations that we needed, right? So, but unfortunately, we don't tell that we have a best approximation with this family.
Okay, so if I got your answer correctly, so there are already existing continued fraction approximations of log2.
Yeah, there is a lot of them. Like,
That's it.
thank you.
У меня имеется вопрос. Вот вы же получали результаты x в нуле, x в точке 1, да? Можете открыть тот слайд?
Да.
В первую очередь, можете открыть функцию x? Я уже забыла вид функции x.
Вот.
Мгм. То есть u зависит, u из n0. Что это означает n0? То есть натуральные числа без нуля или как там n0?
Не, с нулем. То
С
есть,
нулем. Ага.
то есть натуральные числа, включая 0.
Понятно, хорошо. Теперь вот это значение x в точке 0.
Да, то есть вообще...
Дальше вот значение, то, что получили. Вот x в нуле π квадрат на 18, x в точке 1, x в точке 2. То есть ваши вот эти результаты, они убывают или возрастают? Получили какую-нибудь закономерность? Дальше следующие там результаты, всегда в следующих результатах везде появляется π квадрат, верно, да?
Да.
X в точке 3, в 4 и так далее.
Да.
То есть результаты убывают или возрастают все-таки?
Они возрастают, то есть мы можем увидеть, что xu is given by formula, вот по этой формуле, binomial 2u, и поскольку мы знаем binomial, он всегда растет. Получается, репрезентация для u чисел 1, 2, 3, он всегда возрастает.
Возрастает, да?
Да. То есть он всегда...
Ну, например, вот x в точке 2, 12 π квадрат минус 14 1421 делим на 12. Мне кажется, там получится отрицательное число, да?
Вы имеете в виду это? Ну, насчет именно этого...
По x значение у вас возрастает или убывает?
Вот этим вопросом мы не задавались.
Мне кажется, убывает.
То есть я имел в виду, что он возрастает именно...
Да, и к чему-то, да,
интересно.
интересно.
Квадрата.
Интересно, к чему дальше стремиться? Например, x в бесконечности.
Не знаю.
На минус бесконечность получается?
Возможно. То есть это не было нашим главным вопросом, и не задавались этим вопросом.
То есть здесь во всех результатах x в каких-то точках везде появляется π квадрат, да? Угу. Но там общая формула будет для них или что? А общая формула это то, что там сверху написано,
да? Да, вот это общая формула, и насколько мы
π
можем...
квадрат на 18 умножаем на какие-то вот...
Ну да, коэффициент u, где u это, который мы выберем, плюс ρu. Ρ это rational approximation. И судя по формуле ρu, что мы замечаем, тут третья степень, тут получается вторая степень, четвертая степень, то есть эта часть будет меньше, чем вот это, и получается так, что тут минус 13, тут минус 1421, и вследствие я полагаю, что он и дальше будет увеличиваться, то есть...
Хорошо.
Вот 1421, он увеличится еще больше, и мы минус бесконечности когда-нибудь придем.
Да. Хорошо, понятно. Но все-таки надо было чуть-чуть поисследовать. Хорошо. Другие вопросы? Other questions?
Can I ask a question?
Yeah.
Hi, Nurdaulet, hi.
Hi, so I'm very glad to see you.
Yes,
thanks for joining.
Thanks for the invitation. Listen, I was thinking, did you think of, or is it possible to kind of generalize these results by, say, allowing u to be not an integer, but say some algebraic integer in some field extension?
So normally, as far as I know, it can be possible to do so. But we never been working in that approach. We mostly was focused on only integer representations. But as far as I know, like it can be algebraic, it can be rational numbers, complex numbers, whatever you want. But like we didn't research that.
Yeah, it could be interesting if you have maybe there's the binomial coefficients would be related to some values of the gamma function, and maybe you can get some interesting results there.
Yeah, so might be interesting. Maybe I can do second PhD with that.
Okay, thank you.
Следующий вопрос.
Как сюда?
Здесь этот XU к бесконечности как будто не стремится.
Сложный вопрос, особенно если ты не задавался. Но вообще, самое интересное и самое what I'm proud of about this result, то, что сам профессор Кохан не доказал это, а оставил как conjecture, то есть такое. Мы смогли доказать то, что он или не захотел, или не смог. И вот. Это like 1 minute proud moment.
Тут написано, что она π квадрат.
Ну, Кохан имеет в виду, что он converges to p квадрат, только он не имеет в виду, что именно на p квадрат. То есть он обычно имеет в виду там какое-то рациональное число умножить на p квадрат плюс какое-то рациональное число. И вот. Основная его суть, он интересуется вопросом, каким вопросом? То есть converges to constant or not converges to constant. То есть он сходится к какой-нибудь константе или не сходится. Вот он интересуется только этим вопросом. Да? А то, что там рациональные числа, это можно тут сначала добавить, убавить, и у меня получится только π квадрат. Там это не сильно сложно.
Он говорит, что здесь сходится.
Да, ну он говорит, что вот этот полиномиальный continuous fraction сходится к π квадрат. Ну, то есть к какому-то рациональному π квадрат. Но именно к какому он не сказал.
Ну, раз сходится, значит, он не бесконечный?
Да. Если результат будет равно на плюс-минус бесконечность, это означает расходится. Если результат будет какое-то число...
Имеется в виду, опять же, хочется сказать, что бесконечность вот как раз таки исходит из этого момента. То есть сам π квадрат, он и не бесконечен, как мы знаем, но что может сделать его бесконечным, что вот эта часть может стать очень большой или бесконечной, и вот эта часть тоже может стать бесконечной. Что сделает ее как раз таки representation бесконечной? Sorry.
Еще вопросы? Other questions, dear members? Фактическое применение было? Применение.
Да,
этих
применение цепных дробей было в одной из наших публикаций, которая относится к эпидемиологической модели, где мы изобразили коэффициенты вот, continuous fraction как с цепными дробями. То есть we get the best approximation, то есть наилучшую аппроксимацию, и как раз таки это было выражено цепной дробью. И еще известно, то есть не мы это делали, что известно, что цепные дроби относятся также очень близко к теории графов. И недавно, кажется, в 2025 году вышла статья в Symmetry, MDPI, что они как-то его связывали с потоком тока, как-то с электричеством. Как именно, я не смотрел, но суть была в том, что она применялась.
Понятно. Хорошо. У меня следующий вопрос. Когда я читала анкету, вы участвовали в проекте. То есть тот проект связан с этими результатами или тот проект все-таки имеет другую тематику?
Проект и вот цепные дроби, они как раз-таки связаны тем, потому что с проектом мы пытались доказать иррациональность констант. И получается, как раз-таки вот цепные дроби это один из методов, как мы можем доказать иррациональность. То есть они очень даже близко связаны.
Понятно. У меня нету вопросов. Агай, у вас?
Да, все. Other questions, so I think it is enough.
Do you have any questions?
Oh, I can ask. I am the part of some papers.
Okay, so we have our local supervisor, Professor Shynarbek Kadyrov, and please, it's your turn.
Thank you for questions.
Right. Yeah, I'm confident that Nurdaulet Shynarbek deserves to be granted the PhD degree. Yeah, special based on his 3 papers. Basically, I happen to know him. In fact, I was his supervisor in when he was doing his master's also. That's where we sort of started with this project. So this 2023, 2025. So the name of the project was Diophantine approximation and the irrationality of constants. So there are 2 different topics. And somehow we were aware of this Ramanujan machine project from Israeli professors. In fact, we wanted to go there. We were making some discussions, meetings, but then the Palestinian conflict started, so we couldn't go. So Nurdaulet was part of the members. We published many papers related to Diophantine approximation and somehow connection between them. And the first paper that Nurdaulet presented was in fact one of the project papers also about this solving the difference equation and the pi square. The other papers is not directly, I mean, it's not a part of the project. So, what else? So in the first 2 papers, as Nurdaulet mentions, basically we had more or less like an equal contribution with the co-authors, but the last paper, the Q1 paper that he published recently, that's one of his main contributions. So we co-authors basically had some discussion, like we tried to understand together the Cohen's papers. He has many papers on archives. He has like 200 pages encyclopedia or something. So we are trying to understand what he's trying, how he's trying to do with polynomial representation, and so on and so forth. So in the third one, so basically Nurdaulet managed to obtain this representation of pi square following the Cohen's conjecture. So Cohen conjectures that this should work. He said there should be some constant, but he said, oh, this should be very difficult to do it. So he was more or less pessimistic that maybe if anyone can do it. But luckily, so in the first attempt, I think Nurdaulet managed to do it for every u. Like if you give u1, u2, so the algorithm can find the polynomial. So you can do this forever. Like you can run the code. But then, so basically, we were not be able to do the analytic part, like the proof. So that was like a difficulty. We got stuck. But still, I think in this form, the paper already was very strong because it was proving the Cohen's point of view. But then he had the idea of this raising operator. Somehow it converts the u to u plus 1. So if you know the polynomial, this pu for u, then you can do the pu plus 1. Somehow, surprisingly, there was a connection, and in fact, you can find the solution. So there's some tedious calculation going on there. So I think he put it in an appendix or something. So so that was, I think, like a new method. That's a completely new method by constructing an operator. And in number theory, what also interesting is when we have a series, we somehow try to have there's a main part and there's an error term, right? So, and you want to have this error term cancel out somehow. And surprisingly, he also managed to find this telescoping sum, and you get the precise the row, right? So you can find the row. So that was something very interesting. I think very interesting result. I mean, I'm very happy for him. Yeah, what unfortunately is all these things are started from the Appéré. So from 1978, when he made the breakthrough proving the Riemann zeta function, the zeta 3, we now call it Appéré constant, so it's irrational. So his method was constructing a polynomial continuous fraction, but then he had to modify in next step. So he had to modify some part of the continuous fraction to improve the convergence, rate of convergence, and so on. So it's called the Brown-Moore method. And luckily, the cancellations work there because it's small and zeta 3 is relatively small degree polynomials. So it kind of works, some diagonalization method, it works, and eventually he proved. And then people tried to imitate the same method for zeta 5 and so forth. So far, no one could do it. So it seems like a very difficult. So in our project, we hope that maybe we could find a nice polynomial and using the similar transformation tricks, maybe we could eventually get the zeta 5 irrational. In fact, the Professor Sika was also involved in the project as a foreign member. But yeah, I think it didn't work. But still, I mean, constructing the family of continuous fractions is, I think, it's a very important for rational approximation, for speed of convergence. Maybe eventually, maybe one can use those things eventually to prove the irrationality. We hope. So again, I think this is a nice work, and I support Nurdaulet to be granted the PhD degree.
Okay.
Thanks.
У меня имеется вопрос к руководителю. Если смотреть публикации, то есть все публикации имеются авторы, да, то есть все работы были опубликованы вместе с руководителем. То есть в каких статьях студент работал по большей степени сам?
Right. So basically, again, the first two ones, the related to pi squared, the difference equation and the log 2. So it was mainly like again, we were on this project and we were meeting every week. We were doing seminars, reading papers. So these ones we had an equal contribution. So all make the equal contribution, but for the last one, as he also mentioned, like 90% of the work he does. So what I did was maybe to restructuring the paper, maybe suggesting how should he put like the in introduction you should mention the main theorem and so on and so forth. How you should do which part you should move to the maybe appendix to make it a simpler and so forth. So my main contribution was like checking his proofs and basically suggesting how to make the write up. So other than this, I mean, he made all of the work himself.
То есть докторант работал сам тоже, да, как бы?
Struggled.
Да.
Okay. So we also have a foreign supervisor, Francesca Sika from Florida Atlantic University. Please, you can start.
Yeah, so I read what he wrote in his thesis, and in fact, yeah, the last part especially was very, very nice with the answer to the Cohen problems. And at that time, when he gave me the thesis, he was, as Shirali was mentioning, he was still working on generalizing the approach to all integers u, and then at some point he wrote to me that he managed to do that, and that was really impressive. So to me it's a very nice piece of work which shows great skills at technical manipulations, and especially at looking at patterns in these representations, and where it's where it's really not easy to do really. So he has really good skills in this respect.
Okay, thank you. That's all.
And your conclusion is?
Oh yes, he should definitely be given a PhD.
Okay.
Okay, thank you. So, reviewers. So we have two reviewers, and one is Marhabatov Nurlan from Gumilev National University. Nurlan.
Nurlan Agay, are you here? Yeah, thank you.
Қайырлы күн, естіліп тұр ма дауысым?
Естіліп тұр.
Thank you. The work proposes new and well-reasoned analytic and computational methods for the study of generalized continuous fractions and difference equations. The author systematically applies analytic methods, recurrence techniques, and matrix approaches, Möbius transformations, and computational tools to the study of generalized continuous fractions and difference equations. The main results of the work reflected and proven in the author's scientific publications published in peer-reviewed scientific journals and conference proceedings. Based on the quality of the presented scientific work, it is recommended to award Shynarbek Nurdaulet Kairatulu the degree of PhD. Thank you.
Okay, thank you. So the next report by Zaygum Muhammad Asad, Aktobe Regional University.
Okay, thank you very much. Can you hear me?
Yes.
Yeah.
Okay. So Nurdaulet did presented all these results very good today. Also, he has this genuine contribution towards this direction. All these publications, the three he presented today, are of good quality, and I would recommend him for the award of PhD.
Okay.
Thank you.
You. So everything is fulfilled.
Так, есть ли еще там желающие выступить? Вот, коллеги. Дискуссия, это дискуссия, просто обсуждение, уже не вопросы-ответы, а докторанту, просто дискуссия.
У меня есть вопрос такой, я
Мгм.
думаю, я, поскольку не являюсь специалистом в области теории чисел, мне просто интересно вот этот сакральный вопрос Z3, Z5, ну, понятно, вот, что вроде так непонятно, вернее, почему на самом деле исследуется, насколько важна иррациональность? Это либо спортивный интерес, или какой-то есть на самом деле, ну, глубинный смысл, просто хотелось бы понять для себя.
Ну, для меня, я задался тем же вопросом.
Мгм.
Для нас это больше спортивный интерес, то есть никакого, как мне известно, практического значения иррационально Z5 или нет не имеет. То есть, ну, докажем и что. Ничего из этого не поменяется. Но у нас больше такой спортивный интерес, да.
Понятно.
Нет, это хорошо же, если все-таки такие результаты имеют применение, как бы, как сказать, в практике, что ли. Ну, например, вы сказали, там, переменный ток, что-то
Ну,
такое.
да.
Если, как бы, имеют все-таки такие результаты применения, как сказать, в жизни, способствуют там решать задачи, это хорошо решать такие задачи.
Ну, применение, да, а сама иррациональность.
Вот что насчет вот этой зета-функции. Там для любого n зета n является полиномиальным. Ну вот нечетно, естественно, полиномиальным. Или все-таки...
Далеко ли мы от ответа?
Нет, для любого ли n зета от n является полиномиальным вот таким.
То есть для любого можно выразить как полиномиальный?
Можно, да?
Можно, да.
Ага.
То есть, например, для z5 это bn это n в степени 5 плюс n плюс 1 в степени 5. И, конечно, an это умножение этих двух. n to the power of 10, да? n в 10 степени. То же самое можно сделать и 7, и 9, и так далее. Просто единственная проблема, что именно вот это, функция никак не ускоряется, а само наличие этой функции никак не доказывает, что она иррациональна. Вот. Прям из-за того, что степени очень большие, очень сложно с ними работать. То есть уже со степени...
Можно, да, у меня тоже пару мыслей там. Я правильно понимаю, что берем любую вообще пару полиномиальных функций, и она какое-то иррациональное число описывает, правильно?
Ну, не обязательно какое-то, но к чему-то оно сходится. Вот.
Ну,
Именно к константе ли Это не так, это большой вопрос.
So you have a polynomial.
Yeah, if you have two polynomial function,
First question is, does it convert? Not clear. It may not convert. It might oscillate or it may divert. First problem. Second problem, if it converts, is it constant? Is it irrational? Rational? Not clear. It's not clear.
okay.
Да. Поэтому то, что делают, например, Рамонжан Машин, Кохан и другие профессора, они сперва берут полиномиальную дробь, которая известна, например, в нашем случае там π квадрат это 5n квадрат плюс 6n плюс 1, и пытаются искать что-то похожее, например, которое начинается на 5n квадрат, но вот, например, n и однерка, оно меняется. То есть они пытаются искать вот какие-то такие репрезентации. Да. Вот это то, что делает Рамонжан Машин, и в принципе то, что делает Кохан по большей части.
Хорошо, ну, значит, какие-то converge, какие-то diverge, окей. Но все равно же, можно же как-то все вот такие полиномиальные функции, ну, в какой-то в ряд написать как-то эффективно. И какие-то converge, какие-то diverge, ладно. Если converge, ладно, они какое-то иррациональное число описывают. Это означает, что те иррациональные числа, которые описываются этими парами функций, ну, полиномиальных функций, они же не могут быть более чем счетно. Правильно?
Я не понял.
Имеется
Ну,
в
то есть
виду,
все полиномиальные
что
функции счетные.
иррациональных чисел вроде как несчетно,
Да.
а алгоритм у вас, если полиномиальный с
Да,
целыми
она...
коэффициентами, будет давать счетный набор
Да,
чисел. Вот
ну,
в чем вопрос.
значит, какие-то иррациональные числа, которые не описываются такими способом, есть, да, все-таки?
Ну,
Другой вопрос,
получается,
находить их как-то.
Какое именно? Вот насчет этого я не знаю. То есть все константы, которые я знаю, ну, я знаю, не так много имеют, какие-то, возможно, и не имеют.
This thing goes back to Euler, no surprise. So basically there is what's called Euler lemma. If you have a constant represented by any series, you can always convert to continued fraction, polynomial continued fraction. So there is an Euler lemma, simple. It can be done. But if you have some constant that does not have a series representation, does it have a polynomial continued fractions? It's not clear.
Интересно.
Я еще хотел прокомментировать тоже по поводу иррациональности. На самом деле иррациональность – это как бы самый простой фундаментальный вопрос, который вы можете спросить. Там более сложные вопросы – это вопрос про трансцендентность числа. То есть, видимо, ну, эти числа, вот типа z3, оно не только там иррациональное должно быть, просто никто не может, ну, z5 никто не может доказать, а на самом деле оно трансцендентное должно быть. То есть там у чисел, это фундаментальный вопрос математики, там у чисел есть иерархия, как у complexity, как у классов сложности. Там самый простой класс, ну, там типа рациональные числа. Потом идет иррациональные числа, ну, для которых уже тяжело доказать. Потом идет там трансцендентные числа. Трансцендентные числа, ну, это уже там следующий класс. Ну, то есть есть еще иррациональные, есть алгебраические числа. Потом уже трансцендентные. На самом деле все эти константы там, они трансцендентные должны быть. Никто вообще это не может доказать. Ну, там за ним скроется там такая сложная математика, это там алгебраическая теория чисел. Там она связана с модулярными функциями. Там на самом деле большая наука связана с этим. То есть там, ну, это не просто там, что там кто-то там какую-то иррациональность пытается доказать, за ней там большая теория кроется. Там, и там еще есть такая гипотеза, что, то есть если вы возьмете, скажем, z4, z2, z4 в четных числах, они простые константы. Они все такие будут π квадрат, π в четвертой на какое-то рациональное число. А если вы берете нечетные, то гипотеза в том, что вообще оно на π квадрат вообще не делится. То есть не получится там оно с π квадрат линейно независимым будет. Ну, там самый лучший результат, который известен на сегодняшний день, это, ну, есть два результата наилучшие. Первый наилучший результат, это который там еще в 2000-х годах был доказан, что среди вот Z3, Z5, Z7 и так далее есть бесконечно много иррациональных чисел. И второй результат, что если взять 4 числа 5, 7, 9 и 11, среди них есть хотя бы одно иррациональное число. А вот дальше уже никто там не может ничего сделать, там это, ну, достаточно сложно. Там вот они, как бы вот эту методику, которую вот Апери придумал в свое время, как доказать, что ZT3 рационально, они там из нее выжили все по максимуму. Дальше уже ничего не могут сделать. Ну, в целом интересно, вот я думаю, было, конечно, интересно вот для какой-то новой константы вот при помощи ваших методов получить иррациональные сводки хоть каких-то чисел. Ну, там не обязательно, может, там zeta5 или еще чего-нибудь, может, каких-то там новых, ну, каких-то новых интересных чисел. Но в целом хорошая работа. То есть эти результаты интересные.
Окей, хорошо, спасибо.
Спасибо большое.
Так, еще желающие есть? Ну, нет, я скажу, с моей точки зрения, на самом деле, диссертация очень сильно отличается от тех, которые я слышал у нас в Казахстане. У нас любят какие-нибудь функциональные неравенства или уравнения в частных производных, значит, ну или теории моделей, если смотреть ближе туда, либо алгебра в виде всяких там тождеств. Вот. В этом смысле это выдающаяся работа, она вообще особняком стоит. И на самом деле она выделяется тем, что в ней просто оригинальные методы, в отличие от всех остальных работ, где более-менее методы развиты, применяются, и так вариации идут. Вот, эта работа выделяется на самом деле своей оригинальностью, и поэтому особенно интересно. Вот, я поэтому на самом деле призываю членов Совета проголосовать за присуждение ученой степени. Вот мое мнение. Спасибо.
Следующий этап, типа это.
Так, а что у нас
Нет,
дальше там?
если нету как бы желающих выступить на дискуссии, то
Ну, я думаю, достаточно мы послышали, никто против не выступал. Так, у нас процесс тайного голосования, он на самом деле онлайновый, да?
да.
Для всех, и те, кто здесь присутствует, и те, кто дистанционно.
Да,
Причем рецензенты тоже участвуют в голосовании.
да.
Значит,
Вот
и
это-
не участвует только у нас Ширали Кадыров, поскольку он руководитель, лицо заинтересованное. И, значит, остальные все участвуют. Значит, и процедура, я так понимаю, даже
Да.
какая там. Вот сейчас объяснит нам
Так,
процедуру.
у нас будет тайное голосование. Сейчас, так, во время тайного голосования просим других гостей выйти, а также руководителя и докторанта просим на некоторое время покинуть помещение. Сейчас у нас есть как бы группа, туда тоже отправлю или отправлю на почту к те, у кого нету WhatsApp, да. Первыми заполняете Google форму, это как attendance, то, что вы были. Потом будет вторая Google форма, это уже голосование. Хорошо?
Попробуем.
Какой-нибудь председателя счетной комиссии назначать.
Так, да.
Ну, вообще, поскольку, смотрите, электронное голосование, оно автоматическое проводит Google, и поэтому подсчет голосов не требуется. Но формально давайте на всякий случай назначим председателя. Членов-то не надо считать, все равно ничего не надо будет. А председателем я предлагаю назначить секретаря нашего.
Хорошо.
Ну, на самом деле, никакой роли председатель не играет, поскольку там автоматически все считается. Так, можно, давайте проголосуем вот за это. Все, спасибо. Так, ну давайте как-нибудь приступим. Так, что мы должны там получить? Отправили уже?
Аға, жаңағы сөздерді ағылшынша сөйлеуіміз керекпіз дейді неме. Тайное, то есть назначаем председателя дегендерді.
По-английски надо
Да.
сказать. Окей, so we proceed to anonymous voting using the Google Forms and everyone, including reviewers, will vote except one national local supervisor, Shirley Kadil, he will not vote. So all of you will receive a request from Google to confirm your presence. This is the first step, and the second step is real voting. So I think it's okay. Okay.
Окей.
Так, что нам надо тут?
Please. Так.
How are we supposed to receive the forms, the Google Forms?
Steve?
How will we receive the Google Forms?
Так.
It might be sent to your email.
Yeah, I didn't get anything yet.
Since you are the supervisor, you cannot do it. Gauhar солай емес пе?
Even the
Supervisor.
external.
Нет, you are supervisor, foreign supervisor, you can't vote. You can't
I
vote.
cannot? Okay.
Да, да.
Yeah, Shiralan,
Okay.
you cannot. Yeah.
Okay, then I can leave. Then should I leave you? What should I do?
I think in few minutes the results will be announced. So I think you need to
I
again.
can stay. Okay,
Yeah,
I
yeah.
stay. Okay.
Abdul Wahab, did you vote? Can you hear me? Abdul Wahab.
Dr. Wahab is not here at this moment.
Мен қалай өшіремін? Звукты ғана, иә? Неміз қайда бағанағы қағаздарыңыз? Мы сейчас объявим этот результат, потом мына жаққа номерлерін диссертацияны салып қойғандықтан мына бірінші болады, иә, бірінші хаттама. Бірінші хаттама бүгін 29-ы қандай ай? Июль дегенім шілде. 16-шы. Мына жерге ладно аты жөніңізді жазамыз, сосын кеңес мәжілісіне мүше дауыс берді. Иә. Кеңес мәжілісінің кеңес мүшесі. 4 ма или 7 дейін ба? 7. 7 кеңес мүшесі. Кейін дауыс беру нәтижесінде қаншадан дауыс болсын? 8. 0 0 0. И потом, хорошо.
Окей.
Мені, ағай, бірінші мен айтамын. Включили, да, звук? Демонстрацию можете сделать, да?
Все.
Так. Хорошо. Так, окей. Так как председателем счетной комиссии являюсь я, позвольте объявить результаты, да? В голосовании участвовали 8 человек, и 8 выбрали назначить степень PhD докторанту. То есть 8 человек проголосовали за. Здесь не голосовал один член диссовета, Ширали Агай, так как он является руководителем докторанта. То есть 8 из 8 голосовали за 100%. Вот такой результат тайного голосования.
Мы должны утвердить
Да,
результат голосования.
голосуем за результат тайного голосования. Кто за этот результат?
Так,
Остальные
все,
видно,
да?
да, там?
Отлично. Значит, возражающих нету. Ну, тем самым у нас все закончено. Можем поздравить диссертанта и дать ему заключительное слово.
Ағай хаттаманы оқымайсыз ба?
Чего?
Хорошо. Хаттаманы онда мен оқиын ба?
Ну, давай.
Хорошо. Так, бүгінгі қорғаудың хаттамасын оқимыз. Хаттама номері 1, 29 шілде 2026 жыл. Диссертация төрағасы Дайырбеков Нурлан Слемханович, диссертация мүшелері Исмаилов Нурлан Аманкелдиевич, Кадыров Шерали Маратжанович, бұл кісі сонымен қатар докторанттың жетекшісі, Арипова Гаухар Джумабаевна, Елюсизов Тамир Аскарович, Камурзаев Биржан Сейлханович, Абдул Вахаб, Мархабатов Нурлан, Зайгум Мухаммад Асад. Есеп комиссиясы Шынарбек Нұрдаулетке 8-05-401 математика мамандығы бойынша философия докторы PhD дәрежесін алу үшін Computational and Analytic Approaches in Generalized Continued Fractions тақырыбында диссертация қорғау бойынша жасырын дауыс беру нәтижелерін шығару үшін сайланды. Диссертациялық кеңес мүшелерінің құрамы СДУ университетінің ректорының номері 1102208 6 қыркүйек 2024 жылғы бұйрығымен бекітілген. Диссертациялық кеңестің тұрақты мүшелері 4 адамнан тұрады, уақытша құрамы 3 адам болып бекітілді. Кеңес мәжілісінде 7 кеңес мүшесі, оның ішінде қаралып отырған диссертация саласы бойынша қанша ғылым доктор бар бізде? 1, 2, 3. Так, 7 ғылым докторы қатысты. Жасырын дауыс беруге 2 ресми рецензенттер қатысты. Олардың дауыстары диссертациялық кеңес мүшелерінің дауыстарына тең. Жасырын дауыс беру электронды форматта өткізілді. Толтырылған электрондық бюллетендердің саны 8, жарамсыз бюллетендер саны 0. Дауыс беру нәтижесі философия докторы PhD немесе бейіні бойынша ғылыми дәрежесін беру 8, диссертацияны пысықтауға жіберу 0, диссертацияны қайта қорғауға жіберу 0, философия докторы PhD немесе бейіні бойынша докторы ғылыми дәрежесін беруден бас тарту 0. Есеп комиссиясының төрағасы Арепова Гаухар. Комиссия мүшелері осында отырған диссовет мүшелері. Бүгінгі хаттама осы. Ағай, теперь последнее слово докторанту.
Yeah, I think for me it's better to talk in English so that everyone will understand. So thank you, everyone. So first of all, I want to say special thanks to my supervisor, to Shynarbek Kadyrov. In first 2 years, he used to explain everything for me as for a 50-year-old child or sitting with me and trying to explain everything that I know for now. And only last 6 months he was unable for me and said, do everything by yourself. And also I want to say special thanks to him for unstressful or less stressful PhD that I gained. And also I want to say thanks to my external supervisor for helping me much, to Francesca Sica, and he was also very supportive. He helped me a lot. Also, I think overall in this dissertation, in this defense, it's not merely my work, but the work of everyone here, and both my students, my friends that have done a lot of work till now and helped me much. And I want to say special thanks to both of the reviewers and also for sending me these reviews, for writing it, for giving good comments. And also thanks for all participants, committee members who agreed to participate and who came here in their summertime and give a good comments and good approaches. So thank you, everyone.
Окей, good.
Поздравляем, докторантов. Да.
Так, а где мне тут расписаться там?
Ага, чуть позже.
А?
Не уходите. Хорошо, на этом заканчиваем, да, наше заседание. Так, теперь желаем докторанту удачи. Пока что еще не утверждено. Мы будем отправлять документы.